You and I have no problem going from walking to running. It's a natural part of our day-to-day lives. This, however, is not the case for robotic controllers. Last year, we built a simulator to investigate this challenge in robotic systems. In the simulator, a 3x3x1 simple animat must pass a set of obstacles in a tunnel world like this. Its goal is to get as far as possible. This is an example of moving. The animat must move first to find where the gap is located. And this is an example of morphing. The animat must morph into the correct shape in order to pass through an obstacle. The further it gets in the tunnel, the better. This is quantified as a fitness score in our analysis. How does the animat decide to move or morph then? On the animat, there are 5 sensors that provide information to the controller, and it dictates the decision-making process. For starters, here is a visualization of that decision-making process. The animat first receives information from the sensors. Then the controller processes it and makes a decision. In this case, the top 2 sensors detect a wall, while the bottom 2 and the middle sensor don't. This indicates an intelligent controller to either move down or become shorter to overcome the horizontal gap. This is a controller that needs to traverse a vertical gap. It detects a gap from its 2 leftmost sensors and detects a wall from its middle and rightmost sensors. Once again, an intelligent controller would realize that the gap is to the left and would either try to go to the left or make itself thinner. Each of these controllers contain an artificial neural network, which controls the decision-making process. This technique attempts to replicate the idea of a biological brain and its neurons. In this example, we have a neural network with 2 inputs and 1 output. A potential problem that this example network might be trying to tackle is given if it is cold or if it's a weekday, whether or not it's going to be a good day to go swimming. Here we would tell the network that it's cold and a weekday, and it predicts that today is a bad day to go swimming. So how does this work? Starting from the input layer, the values propagate through the arrows to the next layer of neurons. Each neuron from one layer sends its value to each neuron in the next layer. The numbers associated with the arrows are weights, which maintains how strongly the value should be passed to the next associated neuron. When the next neuron receives all the values from the previous layer, it takes the sum, modifies it with something called an activation function, and sends its value to the next layer of neurons. This continues until the final layer indicates what decision has been made. Once again, ultimately, the weights in the neural network are what controls the decision-making process. In our model, we have 5 neurons in the input layer for each sensor, and then 7 neurons in the output layer for each possible action. As you can see here, there are definitely a lot of arrows in which each has an associated weight that needs to be adjusted to make a meaningful decision. So then how does it learn the correct weights? Well, lucky for us, we use a genetic algorithm that solves this problem for us. How does a genetic algorithm work? For starters, we start with a pool of individual controllers in this generation. In this example, we have 9 individuals that start with completely random weights in their neural networks. We then run the simulations for each controller in 3 distinct worlds. For each world, we get a fitness score on how well each individual performed. Then we get the average of these fitness scores to determine the best performing individuals. To make things easier, here are the individuals and the fitness scores right next to them. The first step is selecting the next generation of candidate individuals. Using the tournament selection algorithm, we first take a k-size subset of the population and then get the best individual from that subset. Repeating this process an n number of times, we might select the same individual more than once. However, by first getting a subset of the population, we maintain some level of diversity in the next generation. Let's suppose that in this example, these are the individuals selected by the algorithm. However, there are a few more methods we can use to create a more interesting population pool. First off, there is elitism, which means we make sure that the best scoring individual is always copied on to the next generation unmodified. This is the case even if the tournament selection algorithm didn't select the best individual. This is only done for one controller, in our case, per generation. Just like in biological genetics, we can perform crossing over. In this technique, two individual networks exchange their weights with one another to form two new individuals. These two new diverse individuals become a part of the next population. Now this is mutation, where there is a chance that we slightly change some of the weights in the individual. Individuals produced by crossing over also have a chance to be mutated. And if none of the above is applied to a candidate individual, we can just copy them over to the next population. Then for this example, here is a potential next generation after using the techniques described. We then repeat this process for 2,000 times, which we call generations, and then we observe and extract data from the final generation to see what the controllers have learned. Specifically, we typically look at the best performing controller of the last generation. For these genetic algorithms, we used two different treatments. We wanted to see how each treatment affected the evolution and behavior of the controllers. One of the treatment parameters is called localization. Localization describes whether or not the controller receives information about its relative Z and Y location in the tunnel. Specifically, in the neural network, we'll add two new inputs to process this information. Another treatment parameter is the morph penalty. Morph penalty describes how long the animat must wait until performing another action after choosing to morph. Here are 4 examples of morph penalties side by side. As we can see, the animat with a morph penalty of only 1 needs to use just 1 frame to change its shape. However, for an animat with a morph penalty of 4, it has to wait a whole 4 time steps before morphing again. So the higher the morph penalty, the more this will cut into the amount of time the animat has to get to the end of the tunnel. For every single possible treatment, we ran 20 runs of the genetic algorithm. Each of these runs is seeded to a specific number. We call these runs a replicate since we can replicate the world generation with the seeded number. Okay, so now let's look at the results. But before doing so, let's quick touch on how the fitness is calculated. Fitness is calculated from the number of past obstacles plus the current progress to the next gap by the end of a single world simulation run. Each obstacle passed is 5 units, and the progress to the next is a number less than 5 based on how close it is to the gap. For example, if the animat has successfully passed through 2 gaps and is about halfway to the next, we can expect a fitness for that particular world run to be around 12.5. Also, another thing to mention, keep in mind that the plots I'll be showing take an average of several fitness scores per generation. Alright, so let's get into some of the results. These first set of graphs are called evolutionary plots. It plots fitness against generation, so we can visualize how quickly the animat learns to traverse through the tunnels. We've created 2 separate set of graphs for treatments with and without localization. Treatments are labeled with NL for no localization or LO for localization, and then a number corresponding to the morph penalty time. It seems that as the morph penalty increases, the lower the fitness value will converge at. And then if we look at the 2 graphs side by side, localization doesn't seem to have too large an effect. Here are another set of graphs we've produced. This time, we plotted each generation's best individual fitness scores on the y-axis against the number of times they morphed on the x-axis. Localization, once again, didn't seem to have too big of a difference. So let's just take a look at the no localization graphs. Before we talk further about these results, I'd like to point out something about these graphs. The y-axis has the fitness values locked between 0 and 55. However, for the sake of readability, this is not the case for the x-axis. As we can see, the max morph count decreases as the morph penalty increases here. Okay, so now let's break down what these individual graphs mean. Looking at the graph, as the fitness increases, the amount of average morphs per generation converges at this dot here. The tail seems to represent the controller evolving to use fewer morphs as the generation count increases. We believe that the data points on the right side of the tail represents some of the first generations of the run, and as the controller learns to morph less, this tail is formed until it converges at the dot shown earlier. Going back to the discussion on the point of convergence, the morph count in which each treatment converges at becomes lower as the morph penalty increases. What does that mean? Let's take a look at some of the runs itself. Here is an example of a lower morph penalty run. The animat seems to occasionally morph when nothing is detected. We believe that this is some kind of search strategy that the controller developed in order to reposition its sensors in an attempt to find a gap. This appears to be less prevalent as the morph penalty increases. Instead, the controller seems to favor moving around since there are no time penalties associated with simple movement. This can be seen in some of the heat maps we generated. These heat maps visualize the morph of 20 different runs on the same world. As we can see from the legend on the right, the morph counts are represented by the darkness of this blue color, going from 0 to 25. H shows the relative location of the horizontal gap, while V shows the relative location of a vertical gap. The Z versus X heat map gives a top-down view of the tunnel world, while the Y versus X heat map gives a view of the tunnel world from the side. On these NL1 and NL2 heat maps, the morph locations seem to be almost random. As we can see here for higher penalties, the morphing seems to really only occur when the animat is right next to the gap. So that's only morphing whenever necessary. As a result, the amount of morphs overall is greatly reduced along with the spread of the location of the morphs. We observe that the morph penalty influences the resultant behavior of the evolved animats. In general, the higher the morph penalty, the less morphing will occur. What was surprising to us was the fact that localization didn't seem to have a significant effect. In the future, there may be a few things we want to try. For example, is it possible that a different configuration will allow us to utilize localization more efficiently? What if we tried using a more complex neural network called an LSTM, which has a concept of memory? Hopefully, we'll be able to answer these questions in the future. But that's all we have for today. I hope you were able to learn something new today. Thanks for stopping by.